Welcome to this tutorial on graph theory with SageMath. In this video, we'll cover how to make and display a 2D or 3D graph with specified vertices, edges, and if needed, directions. Then we'll talk about how to make some of the special pre-made graphs that come with SageMath, and we'll go through a few examples of those. We'll then go through some of the functions that SageMath comes with to analyze graphs, including printing the vertices and edges, finding the degree and neighbor of vertices, getting a list of the paths between vertices, getting a shortest path of one vertex to another, etc. And we'll close it out with a discussion of adjacency and incidence matrices and how you can use SageMath to turn your graph into one of these types of matrices and vice versa. So as you'll see in the agenda, we have a lot of ground to cover. Timestamps are in the description if you'd like to jump around. The first order of business is how to display a graph. Now, when I say graph, I'm not talking about an XY plane, a Cartesian model, a function of x equals x plus 1. I'm not talking about that kind of graph. I'm talking rather about something that looks like the following. It is, as you see, a collection of vertices, which you'll also hear called nodes, and these are connected with each other by edges, which are these lines, and they're called edges. And so here, for example, we have one of the many pre-made graphs that come with SageMath. This one happens to be the gem graph, so called because it looks like a gem. And we have vertices, these numbered circles, 0 through 4, so it's 5 vertices total, starting at 0, which is a very Python way to do it. And then they're connected by edges. You see that 0 is connected to each of the other vertices, and then these vertices are connected to each other, and that gives it its gem shape. So, how do we make a graph where we set forth whatever vertices and edges that we want? We set forth our graph using what's called a dictionary in the underlying Python syntax that's behind SageMath. And so the concept of a dictionary, it's not really a graph theory concept, it's a Python concept, but it's critically important that we go through it carefully because it is how you'll probably be making graphs, at least to start. And so what we can do is let's make a variable and we'll call it graph1. I'm just going to delete this out with dd. And let's make a variable called graph1. And we will go ahead and store inside that variable a dictionary that will describe our graph. And there's a couple of ways to make a dictionary in Python, but I'll show you the most typical way first, which is inside these curly brackets like so. And then inside these curly brackets, let's put what we want to be the name of our first vertex. And let's call it A. And make sure you put it in these quotation marks because it's a string. Think of it like plain text, okay? And so then we put a colon. And after that colon, let's put in a list, which is these kinds of brackets, a list, whatever the other vertices you want to be that will be connected to A with an edge. Okay, so let's just do vertices named B, C, and D. All right, and so now we have a dictionary. Okay, and so a dictionary, it has a key of A, and then a value of a list of B, C, and D that's tied in to that key of A, okay? And so that would be what it's called in Python. Or you can think of it as, in graph theory, a vertex of A connected with an edge to B, C, and D. All right? So once again, in Python, we would call the A on the left side of the colon our key, the whole list of B, C, and D on the right side of the colon, the values that correspond to that key, and it's what's called a key value pair. A dictionary is just a set of these key value pairs, okay? And so let's run the cell in order to store our dictionary inside our variable graph1. And then to display the graph inside our dictionary, there's a few things you can do. If it's the last line of a cell in your Jupyter notebook, you can just do graph with a capital G, okay, as a function, capital G. And then inside that function, just put your variable, which happens to be graph1, or you can put the whole dictionary. I could have written this out inside these parentheses, but it's a lot easier to store it inside a variable. And then run it. And now you have your graph displayed, and it's just what we wanted. It has a vertex of A that's connected to vertices B, C, and D, B, C, and D. And you see it has an edge connecting those vertices all to vertex A. There it is. Now, if you've seen my Intro to SageMath tutorial, you might know that the Jupyter Notebook, it's just going to display as an output the last line in a cell. So if I had instead the cell has like a 2 plus 2 on the bottom of it, for example, and then I ran that cell, then all of a sudden, hey, where's my graph? I'm only getting this last line of the cell, and that's because this is just the output. It's just going to give you that last line. So how do I display the graph if it's not the last line of the cell? If I want to get both the graph and also whatever comes underneath it, this 2 plus 2 in this example. Well, you can always add .show, and that's your way of telling SageMath, hey, I want to show the graph. I want to display the graph. So .show with a parentheses, and then it should show the graph, and also it gives me my 4, which is just the reflection of the 2 plus 2 down here. It has nothing to do with the graph. Completely different line of code. So that is graph with a capital G, parentheses. Inside the parentheses, put your dictionary or the variable that you stored your dictionary in, and then .show. And that will show your graph. If you want this graph to display in 3 dimensions, you certainly can do that. And you can do that with, instead of .show 3D. Okay, and then, and I'm going to get rid of the 2 plus 2, it's irrelevant, and run this cell. And now it's going to give me this nice graph. Okay, and you see you no longer have labels on this per se, but it is really nice. I'm actually clicking it with my mouse, and I can move it around. Looks really good. I also, just with the scroll wheel on my mouse, can make it bigger and smaller. Okay. So now let's do an example with a more complicated dictionary that has multiple keys. And let's add a few cells so I can scroll down, maybe zoom in a little. Okay, so let's make another variable and let's call it graph2. And inside this variable, let's put a dictionary. So that's going to remember you're going to have curly brackets. And let's make our first vertex and call it 0. Notice there's no quotes now because a key in a dictionary can also be something like an integer. It can be a string like we had with a, or it can be an integer. It's perfectly fine. And so this will end up with a vertex called 0, okay? And so then colon, and then the different vertices that we want connected to that vertex 0, and this can be a mix and match of letters in quotes or strings, in quotes, or numbers. But just to keep it simple, let's just do numbers. And let's do 1, 2, 3, and 6. So now you're going to have vertex 0 connected to vertices 1, 2, 3, and 6. Okay, these aren't connected to each other yet. That's all that you're going to get. But what if we wanted a more complex graph? Well, then you can do a comma, and then you can put in another vertex, and let's put in vertex 2. Okay, colon, and there can be spaces between the colons or not, it doesn't matter. Colon, and then a list, excuse me, and let's go ahead and make 2 connected to 3, 4, and 6. And then let's make another vertex, 3, connected to a list of, let's just make it 6, okay? And then let's go ahead and do one more vertex to stand isolated, 5, colon, with just an empty bracket to signify it's isolated. It's an empty list, so 5 is not going to be connected via an edge to any other vertex. Okay, and you see how it's all inside curly brackets. You have a key, value, pair, comma, key, value, pair, comma, key value pair, comma, key value pair. Then your values are these lists of other vertices. So this is how you would set it all forth in a dictionary format. Okay, this is not something that was invented for graph theory. This is a Python syntax that exists out in the world. So if it's confusing to you, I encourage you to look at other many videos and other tutorials that involve just Python dictionaries. But let's go ahead and run the cell. And so that stores inside the variable graph2 our dictionary that has our graph. And now let's go ahead and do graph with a capital G, graph2, just to display this graph and see what it looks like. And as you'll see, it's a graph on 7 vertices, and you see how, for example, 5 connected to nothing. Well, 5 is an isolated vertex. It's not connected via an edge with any other vertex. Or, for example, you have 0, which was connected to 1, 2, 3, and 6. Well, 0 is connected to 1, 2, 3, and 6. Okay? 2 is connected to 3, 4, and 6. 2 is indeed connected to 3, 4, and 6. Okay? And see how 0 is also connected to 2? That's because up here, 0 was connected to 2. I didn't need to put 2, 0, because this is not a directional graph. It's going to be connected by virtue of it being connected right here. All right. If you want to have, for example, 2 looped to itself, it's no problem. For example, you can add 2 to your list here connected to the vertex 2, and let's run that. And then let's run the graph again. And you'll see now it's a looped graph, okay? One note about all these graphs, it doesn't matter where, so like the 5 could be over here, and I mean, it doesn't matter where these things are in position to each other. What matters is the way they're connected via edges, and so you can just let the computer take care of how best to display it. But you see now it says looped graph on 7 vertices, and you see the 2 loops itself. But let's go ahead and take that out because we don't really need it. Yes. Okay. All right. So now we're back here. What if you... Oh, actually, one note: if it's looped, the 3D graphing isn't going to work. So you see, if I run it so that it's looped, right, and then I do this, if I do dot show 3D, it's gonna give me an error because it'll be angry with me because it can't do the loop. 3D plotting with multiple edges or loops not implemented. So if you get rid of this loop, and now you just have it show 3D into what it was before, now you see you have a very nice looking graph with your isolated vertex and the other vertices connected to each other with edges, just as you had specified. Okay. So, what if you wanted to label not just the vertices, but also the edges? Looking back at graph 2 here, say we wanted to label the edge. Let's just go ahead and graph 2. I know I just deleted it, but let's bring it back. And so what if you wanted to label the edge between 0 and 1? What if you wanted to label this A? And between 0 and 2, you wanted to label it B. Okay, you can do that. You have to use what's called a nested dictionary. Think of it like a dictionary within a dictionary. So let's go ahead and call this labeled graph 2 because it'll have edge labels, and that'll be our variable name. And then I'm going to actually delete this out so that we can see the comparison between these two. All right, and so now we're going to have a whole dictionary, these curly brackets. Within this dictionary, whereas before we just had this key value pair, key value pair, key value pair, okay? Instead now we're going to have nested inside several more dictionaries. So it'll still be key value pairs, but it will be of dictionaries, and that'll make sense as we do it. So our first vertex, 0, is going to be the key, and then the value on the other side of the colon is actually going to be another dictionary. So we're going to put in more curly brackets, and then we'll put inside that nested dictionary. We're going to put inside the vertices that connect to zero, a dictionary of vertices that connect to zero, colon names for our edges. So if we want the vertex 0 to connect to the vertex 1 as we had before, then colon, and then the name of that edge that will connect the two. So let's call it A. All right. And then comma, then vertex 2, which will connect to also connect to the vertex 0, then colon B. All right. Then comma, then vertex 3, colon C. All right. And so then you close that dictionary off with this curly bracket, put in a comma, and make our next nested dictionary for what's going to connect with vertex 2. So we'll make 2, colon, and then curly for our dictionary, okay, because the value that's tied to this key of 2 is going to be itself a nested dictionary. And then inside this, we can put 3, okay, because remember we're going to have 2 connect to 3, colon D, 4, colon E, 6, colon F, and let's make sure I'm getting all these all in quotes because they're strings. Okay, good. And then you close that off because that was 3, 4, 6, and you see how now each of these has an edge label. Okay. And then we can, so then that's it for that dictionary. And then we can just keep going. So let's do vertex. I think we are on vertex 3, colon, and then curlies. And inside the curlies, let's do 6, colon G. And then that's that nested dictionary. And then finally we have 5, and 5, colon empty curlies, because there's no edge label to do that. There's no edge, right? It's just empty curlies, but notice it's empty curlies because it's still a dictionary. You want this to be consistent. So here it's all lists, and here it's nested dictionaries. Okay. And so let's go ahead and save that into our variable. And then when we graph labeled graph2, if I were just to run this, it's actually not going to show all of these edge labels that we made. So what I'm going to want to do is then do dot show, and inside the parentheses for dot show, you're going to put in a keyword argument to explain to the computer that yes, you really do want the edge labels. And in order to do that, you do edge underscore labels equals true. Okay, and now let's run it and see how it worked. So now you see you have all of your things. Okay, see the 5 is still isolated. You have the 1, and notice it's a different position than it was before. It's, shaped differently, but it doesn't matter. Because what matters is the relation between these vertices and these edges. So you have, for example, 0 is connected to 1 via A. It's connected to 2 via the edge B. Okay, 2 is connected to 4 via the edge E. Okay, so you see how now you have these nice edge labels by way of nested dictionaries. Don't forget to turn your edge labels to true, because by default it's not going to show that. If I just did it like this, then even though I had all those beautiful edge labels there, they're not there. All right, so now these curlies, that's the most typical way that you're probably going to see these dictionaries made, but there is another way that I would like to show you. So let's make some space. Okay, so one more way to make a dictionary is with a function called dict. So let's do graph3 equals dict parentheses. And this is just a function that can make dictionaries. So instead of curly brackets, we have our function dict parentheses, dict parentheses. And inside these parentheses, let's make a list. And inside that list, we'll put in tuples or key value pairs. Okay, so before where we had a key value, key value, key value, now we'll do the same thing, but in parentheses separated by comma. So let's do a key of A, comma, and then for values, let's do a list of B, D, and E, and then that's one tuple, comma, and let's do B for our key, and then let's put in a value of E again, comma, and then let's do one last tuple, and that'll be C, comma, bracket, D, and E. All right. So now let's go ahead and store that into graph 3 by running the cell with Shift Enter or Shift Return if you're on a Mac. And if we graph 3, it will come up with this nice looking graph on 5 vertices. And let's take a look at what we did here. So we have A is connected to B, D, and E, right? A is connected to B, D, and E. And we have B is also connected to E. B also connected to E. Okay. C is connected to D and E. C connected to D and E. It all worked just fine. And so this is actually also a dictionary. If I were just to type it out and run the variable to see what displays, it'll display this in the format we had before with the curlies, because that's what's going to show as default. And so this is the same exact thing as this. It's just a different way of writing it. All these parentheses and brackets might get confusing, so just to break it down, we have dict, and then the outermost parentheses are just the normal parentheses to signify this is our function, what's going to go inside it. And then we have everything inside these list brackets, okay, because what's going to go inside it is just this one list. And then inside of that list are a set of parentheses with one value on one side of the comma and one value. A list is considered to be one value in this tuple on the other side of the comma, or key value pairs. And that's just a way of showing vertex connected to these other vertices. Okay, what if you wanted to make a graph that shows direction from vertex A to vertex B, a directed graph? Well, once again, you can format your directed graph inside of a dictionary. Just take care that the key vertex of your dictionary will be the origin point going in the direction towards the vertices of the values assigned to that key, right? So you would, let's bring back, well, let's actually do a new one. So if we have, I want to be able to scroll up, so I'm going to make some more. There we go. So let's make a variable and call it digraph1 equals, and now let's make a dictionary, curly. All right, let's make a key, A, so one vertex, colon, and then the vertices that connect to it, B, C, and D. Notice this is just the same. If I ran the graph function on this, it would give me a graph with no directions, okay? But I want to make this dictionary display as a directed graph. So instead of graph, like we were using before with the capital G graph, instead of this, we're instead going to do capital D digraph, like this. Capital D, I, capital G, RAPH. And then just the variable. So let's run this to store it inside the variable. And then let's do digraph1, and we can run the variable. And now, notice that you have A, and then it's going towards B, going towards C, going towards D. Look at the arrows, okay? And you can also do a 3D display. It's going to show you with with these arrows. And that's just going to show you the direction. If we change our dictionary here to have, for example, vertex B also going to vertex A, so you have B colon A, and then run that. And now, if we run this, so you see how you have A going to B, but you also have B going to A, okay? And so you have A to B, you also have B to A. And if you want to do show 3D with these double directions to show you, it'll work just fine. And now you have, see these arrows showing in both directions. So it works just fine. Okay, so next I would like to show you some of the pre-made graphs that come built in with SageMath. SageMath has a number of special graphs built in. I certainly won't go through all of these. You can review the documentation to see. But if you type graphs dot and then hit tab on your keyboard, you'll actually come up with a pretty big list of all these different graphs. So just to show you a quick example, let's go ahead and show you butterfly graph. See, I just selected it from the list. It's butterfly graph with the capital B, capital G if you're typing it out. And if I were to run this with these parentheses, it would run, but actually first, let's run it with a question mark instead of a parentheses, just to show you what comes up. If you run it with a question mark, this thing called introspection comes up, and it gives you a whole explainer on what a butterfly graph is, and it will give you some examples, and so all these different things that you can do with it. So that's a nice thing. You can also just X out of it. So if you do this question mark, it'll come up and it'll help you. So if you see something and you think, oh, I wonder what that is, feel free to just, instead of Googling it and looking at the documentation and flipping through that, which is also an option, you can also just do the question mark. But let's run it with these parentheses. So what will actually run, and you see it's a butterfly graph, and it's this nice looking, it looks reminiscent of a butterfly. So there are also some practical application graphs that, perhaps some that would be too big to display, but you can use for analysis. So for example, if you do graphs dot world map, if I were just to run this, it's going to say, well, you can use a dot plot to plot it, but it's 251 vertices, and trust me, you wouldn't get that much value from plotting it. But it has stored in it the countries of the world as vertices connected by an edge if the countries border each other. And that can be useful for analysis. So for example, and we're about to go through some of the functions to analyze graphs, but just for example, if you wanted to see if two countries border each other, that's equivalent on this graph to asking whether there's an edge between the two vertices. So if you have graphs.worldMap with parentheses dot has edge, okay, and then you can do, for example, the names of the vertices, United States, comma, Canada, okay? And that's because these are named vertices in this graph world map, but also we know they border each other, so they're probably vertices that world map as the graph has an edge between them. And if you run it, then it says true, because the countries do border each other, so there is an edge between the vertices United States and Canada. What if we switch the United States with a country that does not border Canada and so probably would not have an edge stored in this map, right? And let's go ahead and do Philippines. False. Okay, so you see, or Mexico. False, right? But if it was Mexico and United States, true, you get it. And that kind of brings me as a segue to my next topic, which is functions to analyze graphs. Let's bring back graph 3 that we previously made. And, well, that's just the dictionary, but let's go ahead and display it so that we can see it. Now, when we display this graph, we can see it. It's it's small. We can kind of comprehend it just from the visual, and we can see that it has, we can see the vertices, we can see the edges, but there's actually various ways that we can analyze a graph without actually displaying it like this. And we can instead, because when you're dealing with a very large graph, you might not want to pull it up and look at it. You might just want to know things about it, right? And so, for example, you could print out a list of vertices, and you can do that by typing at the end of, so if you do graph 3, if you type at the end this dot vertices, and if you run it, it will actually give you a list of all the vertices in that graph. And you see A, B, C, D, E are the vertices in that graph. You can do the same with edges. So if instead you had done dot edges, okay, and you see now it lists out the edges, so from A to B, and none just because we never labeled these edges. So A to B, no name, A to D, okay, and you see A to D, there is an edge there, so this is the list of the edges. And there's no, if we had done the other one we had made before with the edged names, then we would see name there instead of none, but it's not a big deal. You can also pull the degree of any vertex, that is to say the number of edges connecting it. So if you do degree and then a name of one of the vertices, A, see 3, well, are there 3 edges? Well, yes, A has 1, 2, 3, so that's correct. You didn't need to pull it up and count it. You can just do degree to find that degree. Similarly, you can get the neighbors of a vertex. So if you did neighbors, you'll see that D, so you'll see B, E, and D all neighbor A, and indeed B, E, and D all do neighbor A. If you want to list all of the paths between a pair of vertices, you can do that too. So that one is dot, and these are just examples. The documentation has all kinds of things you can do to analyze graphs. I'm just showing you these as examples. So dot all paths C E, and you can see that there's a few different paths between C and E. Or if you want to do one of the shortest paths from one vertex or another, and I say one of because this is only going to give you one, but you can do, shortest path, and it's not going to be that interesting with this one. But let's go ahead and instead let's bring back the world map graph. So that's, let's do graphs dot world map, and then dot shortest path between, let's go with Costa Rica and Chile. Okay, and you see now there's a shortest path between these, and remember, this is not a literal geographic shortest path. It's as if you took a map of the world and put it on a graph so that, each one is a vertex. I mean, the distance between doesn't matter. It's not actually measuring that. It's measuring these edges. And so that's the important thing to bear in mind. This isn't going to give you some geographically accurate shortest path, but it's going to give you mathematically, if this were a graph, the shortest path. And so there's just a ton of things you can do. It's all in the documentation, so I do encourage you to look at that. And so, for example, if you wanted to say, well, what are the different countries that are in the world map? Do they have all the ones? And you can look at it just by doing the dot vertices, and you see there's quite a lot. Well, just from doing the dot vertices, and it's going to list them all out for you. So there's a lot of other things in the documentation that you can use to analyze your graphs, but hopefully that gave you a flavor of the syntax and how you can go about it. The last topic I want to get into today is adjacency and incidence matrices. Let's go back to graph 2, which, as you'll recall, is this dictionary, and let's go ahead and graph it. So it looks like this. Okay, it's got this isolated 5, and it's it's not connected to anything. It's got some other interesting connections. If we took this and did graph 2 dot adjacency, adjacency underscore matrix, okay, and here I'll add some cells so I can scroll up, dot adjacency matrix, and then you ran the cell. Okay, it's going to show that it made it into this matrix, but why did it not return the matrix? Let me see. It's because I need to put parentheses. There we go. Okay, so the mistake I was making is that I did not put parentheses at the end there. And so in any event, all right, so you see you have graph 2 dot adjacency matrix. And this it's going to return this matrix, and this is what's called an adjacency matrix. It just says if we were to label the rows and columns of our vertices of our matrix here, if we were to label the rows and the columns, each one as one of the vertices. So remember in this example we have vertex 0, vertex 1, okay, through vertex 5. So if this were 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6. So I guess this one also goes up to 6. So 0, 1, 2, 3, 4, 5, 6. So just kind of visualize that in your mind's eye that we're labeling the top and the side here. And then we were just to ask, is one of these vertices connected to any other of the vertices, right? So is vertex 1, okay, which is, say this second column, vertex 1, is that connected to vertex 3? So that'll be 0, 1, 2, 3, vertex 1, so it should be no, because it's a 0. So if it's 1, then it's connected by an edge. If it's a 0, it's no. So what was that, 1 and 3? And we see indeed it's true. 1 and 3 not connected to each other by an edge. 5 is isolated. Well, sure enough, 0, 1, 2, 3, 4, 5, all zeros. Same here, all zeros. Not connected to anything, zeros across, zeros down. All right, and so that's a way of taking a graph and representing it in a matrix, and that's very useful in a lot of cases. So you'll see a lot of use cases of this, but it's especially if you're going to be working on this on your computer. What if you have an adjacency matrix and you want to turn it into a graph? Well, you can actually just use the graph function. So let's make a matrix called A, and let's have A equal, and if you're not familiar with how to make a matrix, I have a whole video on that, so we'll put it on a link. But one way to make a matrix is you can do a matrix with one row that's 0, 1, and one row that's 1, 0. So just to do something very simple. And then if I were to run just this matrix, you would see it's very simple, 0, 1, 1, 0. Okay, so what does this signify? Well, then you would think, well, 0, this first vertex is it's not looped back to itself or anything, but it's connected to the second vertex. And you would see that both ways, okay? So if you were just to do graph, and you can just graph that matrix, and there it is, 1 and 0, just two vertices connected by an edge. And so that's one type of matrix, and that's the adjacency matrix. And you can turn a graph into that, or you can turn an adjacency matrix into a graph. A different way of representing a graph with a matrix is something called an incidence matrix. And so if you go to, let's go back to graph 2. If you do graph2 dot incidence underscore matrix, now you see you actually have a different matrix. Even though it's the same graph, you have a different matrix. And if you just visualize in your mind's eye that each of the rows is one of the vertices, 0 through 6, each of the columns is one of the edges. So there's a 1, the vertex belongs to the edge, 0 if not. So for example, see how the vertex 5 is straight zeros because there's no edges, because it's an isolated vertex. Okay, so that's just an example. And so it's just another way of making a matrix representation of a graph. If so, you can turn any graph into, well, you can turn a graph into an incidence matrix. Um, you can also turn an incidence matrix into a graph, but it's a little trickier because if you just do graph of a matrix, it's going to assume it's an adjacency matrix. So you have to be very clear to SageMath that no, this is not an adjacency matrix, it's an incidence matrix. And so if you were to store this into a variable m, okay, and then say you have graph of m. If I just left it like this, it's not going to know. Okay, so I have to do comma, and then the keyword argument format equals incidence underscore matrix. And that's critically important. And so then if I run it, and it'll give me my graph. Okay, and the positions of these vertices doesn't matter. What matters is the relationships. And so you see it's the same, 0 connection to 1, etc. You know, with 5 on its own. Okay, and so that wraps up this tutorial on an intro to graph theory with SageMath. I do have more SageMath content coming, so if you're interested in that, please do subscribe, and I want to thank you very much for watching.